Hello and welcome to Silicon Innovation at AWS. My name is Ali Saidi. I'm a senior principal engineer and the lead engineer for our Graviton instances. Today I'm going to talk to you about some of the silicon we're building and why we're building it. With me today, I've got Ron. He's my colleague on the machine learning side, and he's going to take care of the later half of the talk, even though his name isn't on here. So far, we've built chips that span multiple areas, including data center and I/O, infrastructure, core compute, and machine learning. With the Nitro system, we were consuming more and more of the resources on the host CPU for hypervisor functionality. The hypervisor is the piece of software that takes a big server and cuts it into smaller virtual machines. And so we started moving that functionality away from a traditional hypervisor onto special purpose chips. We started that journey back in 2013. And later, working with a startup named Annapurna Labs, which AWS would later acquire, we moved more and more of the functionality out of the hypervisor onto special purpose silicon. This freed up the host CPU for more of your workloads, and let us raise the bar on security for our servers. Then with Graviton, we built a host CPU that provides powerful and efficient compute for a range of workloads in EC2, as well as the best price performance in their instance families. And lastly, with Inferentia and with Trainium, we have purpose-built machine learning accelerators we built from the ground up, one for inference with Inferentia, and you can guess the other for training with Trainium. I'm going to talk about each of these in turn, but first I'm going to spend a little bit of time talking about why we're going through all the work of building silicon here. And the answer is really simple. We're building silicon where we have a way to deliver more customer value when we do it. And there are a couple of ways that we do this. The first is through specialization. By building our own chips, we get to specialize the hardware for the use cases we have in AWS. It lets us really tailor the designs to operate in our environment and focus on the features that we need to deliver value for you. And you might say, well, of course you do that. But when a third party is building a chip, they want to satisfy as many different customers as they can. And so they need features for them all. And that means they need to add the complexity, the cost, and the power for all of those. When we're building chips for our use cases and the use cases we can deliver value to you, we get to focus on the ones that we actually need. So I'll show you today how we've tailored the Nitro system to AWS's infrastructure and to improve the performance and security of our servers. The second is speed. By building our own silicon, we get better speed of execution. And there's a couple of different dimensions here. The first is what I just mentioned, actually, specialization. By focusing on the features that we really need, we can focus on that one market. We don't have to burden the design with other complexity that will take longer to deliver. The other is by owning the end-to-end development process, defining the product, the silicon we need, the chips we need to deliver it, when we start that project, and being able to have the teams working on the hardware in parallel, have the teams working on the software. So that when the hardware is ready, the software is ready as well, and we can deliver both of them to you very quickly. That means there's less handoffs, the software and hardware team runs in parallel. Also, building chips and silicon requires an immense amount of simulation of the logic, simulation of the physical design. And by actually using EC2 and the elasticity that EC2 provides, we can burst into an amazing amount of compute when we're reaching milestones to make sure that we do all the simulations that we need in a timely fashion. The third is really innovation. By building our own chips, we get to innovate more and create more value. And the reason for this is we get to cut across traditional silos. Traditionally, you have a chip vendor, a server vendor, a software vendor, and each one of those people are making great decisions, but they're making it at the boundaries of what they're delivering. And by being able to look across the entire design, you might decide to spend maybe more on a chip so you can spend less on a server. And the traditional silos might not allow you to actually do that. And lastly, security. Nitro provides us a mechanism to enhance the security of our servers by offering a hardware root of trust, verification of the firmware running on them, and limiting the interactions to the host through a narrow set of APIs. Let me start with the Nitro system. And Nitro is really a fundamental rethink about how virtualization should be done. And it really started with us saying, if we took our learnings from running EC2 for almost a decade, what could we improve? And there were a lot of things that we thought we could improve. We could improve throughput to reduce the cost of running your workloads. We could simplify the hypervisor, remove complexity, and get bare metal-like performance. We could reduce instance latency and jitter, which would allow you to bring more workloads to the cloud. And we could even build a system that would allow us to offer not only virtual machines, but the same set of experience with attaching and detaching volumes, starting and stopping instances dynamically from bare metal servers as well. On the security side, we could use it to offer things like transparent encryption of data in a VPC, that harder root of trust I mentioned, removing operator access from the system, and having a narrow set of audible APIs. And Nitro gave us a path to implement all of those. Nitro is a combination of purpose-built hardware built exclusively for and by AWS, and the software that runs on that. We've been doing this for a while now. We're on the 5th generation of our Nitro chips. Peter introduced the 5th one back on Monday. And we introduced the first one back in 2017 when we talked about the C5 instance. It's been 5 years since we did that. But really, this journey started in 2013, where we launched enhanced networking. And we started moving some functionality out of the hypervisor. And that's that piece of software that takes a big server and cuts it into virtual machines. And started moving that on to into hardware. And that let us offer higher performance, better latency, improved CPU utilization. Over time, we expanded this to other types of I/O, to EBS, to local storage. And eventually, what we did was we rethought of what our hypervisor should be. And we removed a bunch of functionality. Since 2017, every instance we've launched has been based on the Nitro system. And to understand the transformation here, it makes sense to start with a little bit of what this looked like before Nitro. This is what one of our servers looked like before Nitro. And customers are still using some of these instance types today. People are still running M1s and similar. And here we have a hypervisor called Zen. Zen's great, but it did a lot. It did memory management and CPU scheduling. It did device emulation. It did limiters. It did security groups, enforcement. It did quite a bit more than that as well. It even has a full-blown Linux user space in this privileged DOM0 you see here. And all this functionality used resources on that host CPU that customers couldn't use. So we started moving some of that functionality off of the host. And we did this with our Nitro cards. We've got cards that offload the VPC, EBS, Nitro SSDs, and various system control functionality. The VPC is the first one we did, so let me talk about that one a bit. The VPC data plane offloads your ENI attachment, security groups, the packet encapsulation, encapsulation we do, flow logs, routing decisions, DHCP, DNS, and more. All those functions used to run on that hypervisor, and we move them off. Our newer versions of Nitro cards also support VPC encryption, where you transparently and without a performance penalty encrypt your VPC traffic with AES. The VPC card presents the ENA device that you might have seen in your instances. That device started by offering up to 10 gigabits of bandwidth when we first announced it. And over time, we've gone up to 200 gigabits with that same device model, that same driver. It's a 20x increase in performance without having to tell you to go and change your drivers, build new AMIs, or anything like that. And that's pretty unique. I can't think of another place where we've seen a 20x increase in performance without having to change your drivers or change the device model. This week, we also announced ENA Express. ENA Express lets you take TCP, which is an end-to-end protocol between two of your instances. And instead of just following one path through our network in our data centers, take that traffic and send it down many paths. This lets you use more of our network, find lower latency paths, and reduce latency from between two instances by as much as 40%, the P99, as well as increase the single traffic flow between two instances by 5x. We also have the Elastic Fabric adapter. This is a network interface that's focused on machine learning and HPC workloads. These workloads are a little bit different in that usually you have a workload that's either low latency or it's high bandwidth. But with HPC and machine learning, you typically have a workload that's both. It needs high bandwidth and it needs low latency. And so we built EFA that allows applications to bypass the kernel, talk straight to the device, and get that low latency and high performance. And just like ENA Express, you can use multiple paths through our network to get high bandwidth and low latency traffic between your instances. The other Nitro card I'll talk about is the Nitro SSD. And before I talk about that, though, I need to tell you a little bit about how an SSD works. And there are two main components in a traditional SSD that are interesting. The first is the NAND. This is where the bits are stored. And NAND is a little peculiar, that you can only write it after you've erased it. That kind of makes sense. But you have to erase it in chunks of megabytes. So even if you want to just change a word in a file, it means you really have to copy that file to a new location and then clean up the old file later. The other interesting thing about NAND is it wears out. The more you write to it, it eventually gets slower, and then it's unable to store the data anymore. And so you don't want to write to just one location over and over again. You want to move those writes around all of the NAND. Now, that's complex to do. And so there's this other chip called a flash translation layer, an FTL. And it takes care of this complexity. The operating system has a logical address of where it stored something, and the FTL knows where that was. It deals with that where leveling. It deals with the garbage collection I just mentioned. And really, it actually looks a lot like a write-ahead logging database in the end. And like most databases, as you go to different vendors, you get a different implementation. They all do a pretty good job on the average case, but when you push them, they behave a little differently, sometimes at the worst time. Maybe you've got a high bandwidth database and the garbage collection kicks in just when you have a traffic spike. So we looked at this and said, well, how can we get consistent performance from different vendors and devices? You're probably guessing where I'm going here. This is a rendering of a Graviton 2 storage server, and you can see the NAND there with the heatsink on top. So we took that NAND and we added a Nitro card. And the FTL runs on that Nitro card. And the results here are pretty spectacular. The I4I, the IM4GN, the IS4GN instances lowered average I/O latency by as much as 60% and lowered tail latency by 75%. This improvement allows you to run more intense workloads with stricter SLAs, but it also has allowed customers to run at higher load than they were previously and get better cost savings versus our i3 and i3n instances. One such customer is Splunk. Splunk's a leading data platform provider designed to investigate, monitor, and act on data at any scale. When they evaluated IM4GN and the Nitro SSD, they observed up to 50% decrease in search runtime compared to their i3 and i3ens. So we took that I/O from that traditional picture and we moved it off onto a Nitro card. You can see that DOM0 there, that privileged domain in the Zen world, is significantly offloaded. Many of its functions are now on Nitro cards. And so we could step back and say, what do we need the hypervisor to do? Really, we need to do two things. We needed to do memory and CPU allocation. The rest, they can just get out of the way. And that's what we ended up building, a hypervisor that provides bare metal-like performance with its reduced size and complexity. Lastly, we added the Nitro security chip. These are integrated onto our motherboard and provide a simple hardware-based root of trust that lets us measure the contents of the flash devices on our system, prevent unauthorized modification, and make sure that we're running the firmware that we think we are. So with all of this now, we could remove DOM0 and replace Zen with the Nitro hypervisor and enhance the security posture of our servers. We designed the Nitro system to provide workload confidentiality, not just between customers, but also between customers and AWS. There's no mechanism for any system or person to log into these Nitro instances and access customer data. There's no root user, there's no interactive access, there's only a narrow set of authorized and authenticated APIs that don't have access to customer data. We recently published a white paper on this, with the security overview of the Nitro system, and you can find that online now. We've been building silicon, as I mentioned, for quite some time. And a couple nights ago, we announced the 5th generation of our Nitro card. This one has 22 billion transistors, nearly double that of our 4th generation. It supports DDR5 and PCI Gen 5. We've gone from supporting encryption on the network device to adding encryption to DRAM and adding encryption to support for PCIe with our 5th generation of Nitro card. The device increased the packet rate by up to 60%. Has up to 30% lower latency, and did all that while reducing power, actually. I've talked about performance, and I've talked about security, but there's one more aspect to the Nitro system that I wanted to share with you, and that's really, it's a modular design. It's almost like a Lego block of components. We've taken the same Nitro card that we started with in an Intel server. We've moved it to an AMD server. We put it in a Graviton server. We even connected to a Mac Mini and offered the Mac 1 instance type. All without changing the cards. It took us 11 years to go from 1 instance type in 2006 to 70 instance types in 2017. And since then, we've gone from 70 to around 600 instance types. And the reason we're able to do that is what I just mentioned, that we've taken our Nitro cards and we've put them in different servers with different storage, different architectures, different CPUs, different accelerators, and provided you a large amount of flexibility to choose the optimal instance for your workloads. Okay, so we've talked about Nitro. Let me talk a bit about Graviton. Graviton's our line of ARM-based server processors available exclusively in AWS that provide the best performance and price performance in their instance families. And we started this journey back in 2018 when we announced the first Graviton processor. We didn't even call it Graviton 1, it was just Graviton. And a lot of people looked at us a little strangely then and said, well, what are you doing here? But Graviton proved that you could have another architecture in EC2, that you could run different AMIs, you could start and stop instances, you could see the same elasticity you saw on x86 instances. You had wide iOS support. And it wasn't really, though, until Graviton 2 in 2019 that people said, oh, this chip has 6 times the transistors of the first Graviton, 4 times the cores. Each core is about twice as fast. And we went from kind of a curiosity and it's interesting, I wonder why they did that, to some of the best price performance in EC2. And we haven't stopped there. With Graviton 3 last year, we've almost doubled transistors again, a huge step up in performance. I'm going to talk about Graviton 2 a little bit and then talk about Graviton 3. As of today, we've got 12 different instance types across our different families powered by Graviton 2. The M6G and M6GD support general purpose workloads, one with local storage and one without. We have a burstable T4G instance, and there's still a free trial on T4G smalls. If you haven't tried one, you can try one. We've got the compute, memory, intensive types, and also a C6GN for network intensive workloads like load balancers and firewalls. The IM4GN and IS4GN for storage workloads with those Nitro SSDs I mentioned earlier, and even one with GPUs that we've seen people use for rendering, Android emulation, and machine learning. These are all available between 1 and 64 vCPUs, now across 28 different regions worldwide. One of the simplest ways to consume Graviton is through our managed services, because they expose the same API if they're running on an x86 or they're running on a Graviton. So typically you can just change the underlying instance type and not have to change your code. We've got 6 different databases now: DocumentDB, Aurora, RDS, Elasticache, MemoryDB, and Neptune, some of which offer Graviton by default. We have a few analytics offerings now on Graviton as well, including OpenSearch, EMR, Compute with Lambda, Fargate, and Beanstalk. And just a couple months ago, SageMaker also announced support for Graviton. And we've seen customers from large enterprises to startups across different verticals, segments, and geographies all adopt Graviton-based instances in Amazon EC2 or those managed services. Tens of thousands of them now. And they typically just start with one service. They found something that they run a lot of and tried to move it. And most customers told me it was actually easier to move than they thought. The hard part wasn't actually recompiling it. It was more in the pipelines that they have to build artifacts and deploy them. That was the thing that they had to work out. Once they worked that out, the code compiled, it ran, they were happy. We've had people like Discovery use Graviton-based EC2 instances to reach 175 million viewers during the Tokyo Olympics. DirecTV, who did what I said and started with a single Go service, and now are running hundreds of Go services on Graviton. We have people like Epic Games, who are running Fortnite in the Unreal Engine on Graviton, and Intuit, who moved Kafka workloads to Graviton. Graviton also offers energy-efficient compute. NEC and Docomo have been recently collaborating on a 5G core workload, bridging Docomo's on-premise infrastructure with NEC's 5G core workload running in our regions. Not only did they find great performance, but they also said, we were delighted to announce that we've achieved significant reduction in power consumption of the 5G core thanks to NEC's advanced cloud-native 5G software and AWS's innovative and highly efficient Graviton 2. With Graviton 3, we've continued that journey. It's obviously our third generation chip. It looks a little different in that we've added 7 different chiplets here. The transistor count has almost doubled to 55 billion transistors. And it's the first system in our data centers that had DDR5 memory. Now, Graviton 3 runs at a slightly faster clock, but gets most of its performance by extracting more IPC, or instructions per cycle. Those 30 to 55 billion transistors, well, I can tell you where a lot of them went. We made the cores bigger. The cores have a 2x wider front end, a much bigger branch predictor that predicts branches better for large workloads, a 2x wider dispatch, a 2x larger instruction window, twice the SIMD bandwidth, including things like bfloat16, which are applicable to machine learning workloads, twice the memory operations per cycle, twice the number of outstanding transactions, twice the number of ALUs. And all this gives you 2x the performance on things like TLS negotiation, as well as some security features, like pointer authentication, which is a way that can prevent return-oriented programming attacks, and RNG instruction that lets you get random numbers from user space. Now, Graviton vCPUs are a little different than the vCPUs on x86. x86 systems support simultaneous multithreading, or SMT. What this means is those 2 vCPUs end up sharing some physical resources in the core and the caches. And so if both CPUs aren't busy, that's great. It's higher efficiency. You get to timeshare that core effectively. But as the systems get busy, now you're just time slicing them. And you're seeing contention in the cores and the caches. This is why some people see, as they push CPU utilization above 50%, their P99 latencies start increasing rapidly. With Graviton, every vCPU is its own core. They don't interfere with each other. Not in the core, not in the L1 caches, not in the L2 caches. It provides a stronger security boundary, and it also typically lets customers push their load on Graviton higher without sacrificing latency, and thus reducing costs. This is what a Graviton 3 CPU looks like. And we started with a big die. We put 64 cores on there. We connected them together with a mesh that's running at over 2 gigahertz. It provides more than 2 terabytes a second of bisection bandwidth. And then we distributed 32 megabytes of last level cache around that mesh, which would be super high bandwidth. With that cache and the private caches of the cores, there's over 100 megabytes of last level cache in the processor. We have our DDR5 controllers, 8 channels of DDR5, 300 gigabytes a second of theoretical bandwidth, and really easy, accessible bandwidth. You just have simple loops. You end up getting that theoretical bandwidth. Excuse me. And just like Graviton 2, we encrypt all the DDR interfaces. And lastly, we have PCIe. We've done other innovations there too. Traditionally, when a device interrupts a VM, it goes through the hypervisor. This is okay, but that trip through the hypervisor increases latency. And so with Graviton 3, and then later actually with Graviton 2, we bypass the hypervisor and send the interrupt directly into the VM. That improves latency, but since we're also not actually ever getting to the hypervisor as well, it also improves throughput. The C7G instance is the first instance based on Graviton 3. It provides up to 25% higher performance than the C6 instance, the one based on Graviton 2. And it has those things that I mentioned, twice the floating point performance, twice the cryptographic performance, ends up to 60% more energy efficient versus comparable EC2 instances. We've seen lots of customers run at-scale data processing workloads in Graviton 2. So we want to see what that looks like on Graviton 3. Here we're running Spark SQL with Spark 3.3 and AWS Graviton 17 with an 8-node cluster and a 1 terabyte data set. And compared to Graviton 2 on a C6G, Spark SQL is 28% faster. So in a single generation, we've gone up by 28%. We also looked at applications like Node.js. Here, we fixed a load generator, and we fixed a database. And we either put a C6G or a C7G running Node. We're running this sample application called Acme Air that has flight scheduling. And going from a Graviton 2 to a Graviton 3, we see 37% performance increase. We have a lot of customers who are doing video encoding. And so AWS and the open source community have been spending time improving video encoding on Graviton. And over the past year, we've made a huge improvement. Going from an older version of MPEG to the latest, we've seen a 60% increase in performance. Then on top of that, going from Graviton 2 to Graviton 3, we see a 50% increase in performance. So well over 2x from where we were a year ago. The same is also true for machine learning. Here, there's a lot of code where people have lovingly hand-optimized the machine learning code. And AWS, along with ARM and others, have spent a lot of time working on TensorFlow, PyTorch, 1DNN, and the ARM Compute Library to improve the performance of machine learning on Graviton. You can see some of the numbers going from Graviton 2 to Graviton 3, where we added bfloat 16 and the SIMD units. 2x, 3x type numbers. Really big. So we started with the C7G instance. And this week, we've announced 2 more. The C7GN, which is for network-intensive workloads, up to 50% higher PPS and 2x higher bandwidth than our other networking instance types. This features that 5th generation Nitro card that I talked about earlier in the talk. And also HPC7G, an instance focused on high-performance computing workloads. This one has our Graviton 3E processor, which is a variant of Graviton 3 that does more SIMD operations per cycle. So when we built C7G, we were really focusing on the mainstream workloads. We wanted to optimize power consumption. But HPC workloads are a bit different. They can have a lot more vector math, a lot more linear algebra. And so when we looked at and wanted to offer HPC7G, we said, well, what can we do here? And we found a way to increase the SIMD performance over where we were with Graviton 3 and the C7G. With this, we've seen 10% on molecular dynamics workloads like GROMACS, 30% on HPL, and somewhere in the middle on some option pricing workloads. Now, our innovations didn't stop with just the chip. We have end-to-end ownership of these systems. And typically, in a data center, you've got racks, and the racks are about 42 U tall, and then they're full of 2 socket servers. Each one's 1 U. And traditionally, you run out of power in a position before you run out of space. But with Graviton 2, we had the opposite problem. We'd run out of space in the rack before we would actually run out of power. So what can we do? Well, when we sat down to build Graviton 3, we designed the chip, the package, and the motherboards to not have 2, but to have 3 sockets in a single one-use server. This increased the socket density by as much as 50% in the rack. It came closer to the power requirements of some other solutions. And because we also own the Nitro card, we developed it so it could manage 3 sockets at once, not just 2. So with that, we have what a Graviton 3 server looks like. And we've had some great customer feedback on this. The first is Nextrol. They're a marketing technology company. When they moved from C6G to C7G, they saw 15% higher performance. That's not what excited them. What excited them was at the same time they saw a 40% reduction in latency. And that was really important for them, for their workload. We have Sprinkler, who provides a unified customer experience management platform. When they moved to Graviton 3 from Graviton 2, they saw 27% better performance. Ansys, which does industry-leading physics-based simulation, they have a product called LS-DYNA that does crash simulation. And when they moved from Graviton 2 to 3, they saw 35% higher performance. And lastly, Viant, an advertising company, saw 45% higher performance when they moved from Graviton 2 to 3 with their compute-intensive, one of their compute-intensive workloads. Okay, thank you for tolerating my voice. I'm going to hand over to Ron now, who's going to talk about machine learning.
Hey folks, thanks for being with us today. So our third product line, and it's actually 2 sibling product lines, are AWS Inferentia and Trainium. As Ali mentioned, Inferentia provides you with best-in-class performance and price performance for inference workload, and Trainium does the same for training workloads. So we built Inferentia and Trainium seeing the massive explosion of AI workloads in recent years. And it's not only that AI is becoming more popular, but models are becoming larger, and they are becoming larger because the larger models are more accurate, and that means that training becomes more expensive, inference becomes slower, so we figured that we have to do something to help you get more out of AI and reap the benefits of the AI progress in recent years. So we built AWS Inferentia, again, for inference workloads and Trainium for training workloads, but we wanted to make the migration in and out of Inferentia and Trainium as easy as possible, and that's why we built the Neuron SDK. The Neuron SDK integrates Inferentia and Trainium to popular machine learning frameworks like PyTorch and TensorFlow, making it super easy to compile and run your favorite machine learning models on these targets. You just add, it's literally 3-4 lines of code, and it compiles and runs seamlessly on the hardware. And we make it a priority. Our goal here is to provide you with high performance out of the box, without needing to change your models or do any performance tuning efforts. We announced our first instance back in 2019. It's called the Inf1 instance, and the Inf1 instances are based on our first ML silicon called Inferentia. We efficiently pack 16 Inferentia devices in a single server, and that's possible because, again, we own the end-to-end and we drive the power of Inferentia very low. And with 16 Inferentia devices in a single server, Inf1 delivers with 1 petaflops of bfloat16 or FE16 compute and 2 petaops of int8 compute. Now, it didn't make it into our slides today, but this week we also announced Inf2, based on Inferentia 2, which delivers 2.5x more compute performance and 15x more memory bandwidth. So a massive increase between generation 1 and 2 here. Let's look at end-to-end performance with Inf1. Compared to our next-in-line inference-optimized server, which is G5 based on GPUs, Inf1 delivers 25% higher end-to-end performance and up to 70% lower cost per inference. So that's a massive improvement that you're getting by just switching your workloads from GPU-based instances to the Inferentia-based instances. And we're seeing thousands of customers that are using Inf1 today. We have enterprise-level customers like Airbnb and Snap. Airbnb reported that when they migrated their chatbot from a GPU-based instance to Inf1, they saw a 2x performance improvement out of the box, again without needing to change their models. And we also have enterprise customers like NTPC and Condé Nast, and also several fast-moving startups that are all migrating from other inference instances to the Inf1 instance based on Inferentia. In addition to that, Amazon teams are also migrating their services to the AI inference services to Inferentia. Most recently, Amazon.com moved their search from GPU-based instances to Inf1, and they saw an 85% lower cost while also reducing their latency at the same time. And this is pretty significant. Typically, you get only one of them and not the two together. All right, we talked about Inferentia. Let's move to talk about Trainium. With Trainium, we did the same that we did for Inferentia, but for training workloads. Now, training workloads are different than inference workloads. They require a massive amount of computations, typically running for a very long time, and very often running on clusters as well. So that's why you see that the spec is quite different here. We again pack 16 Trainium devices, our second generation machine learning chip, inside a single TRN1 server. And here we deliver with 3.4 petaflops of bfloat16 compute, same for FP16 compute, and also 840 teraflops of float32 compute, and I'll touch on that later. That's an interesting point. They also come with 13.1 terabyte per second of memory bandwidth. So that's an extraordinary number. And again, this is critical when you dealing with training workloads because they tend to be very memory intensive. And as a last point here, TRN1 instances come with 800 gigabit per second of network bandwidth based on EFA v2. This is important, especially for scale-out training, where when we train a single model on multiple servers. And to double down on that, coming soon is TRN1N, where we attach 1.6 terabit per second for every single instance. As I mentioned before, models are becoming larger very quickly. They're actually increasing in size in recent years by about 10x per year, especially when talking about the large language models. And that means that when training state-of-the-art models, you actually need to train on hundreds, sometimes thousands, and in the state-of-the-art cases, tens of thousands of devices in a single training task. And this is quite challenging. So to handle that, we built the TRN1 and TRN1N ultra clusters. These ultra clusters pack more than 30,000 training devices in a single data center with non-blocking petabit scale EFA interconnect between them. So just think about the scale, 30,000 devices in a single data center with non-blocking interconnect. We deliver with that capability 6 exaflops of highly optimized machine learning compute. And you can scale it up and down and get elasticity at a supercomputer level. So that's quite a significant offering here. Stepping back here and looking at that end-to-end performance, TRN1 delivers 1.5x the performance and half the cost to train compared to our next in-line ML training instance called P4D. Let's dive a little deeper into the Trainium features that make all of this possible. And we'll start with data types. Machine learning workloads require a massive amount of floating point calculations. And these calculations vary in range and precision, starting from float32 through the popular float16 and bfloat16, and all the way to a new emerging configurable float8 data type. Now, different neural networks require different data types to reach their optimal accuracy. And moreover, during earlier research and discovery phases, ML scientists typically prefer the float32 data type for its ease of use and accuracy. But then, as they move to train at scale, they'll typically go with a more compact data type, like bfloat16, in order to optimize for price performance. And this is especially true if this is one of the giant models that are costly to train. Trainium comes with a very rich set of data types, just like you see on the screen, in order to allow you to select the most optimal data type for your specific use case. And in terms of compute performance, TRN1 delivers 40% higher bfloat16 performance and 5x higher float32 performance compared to our next in-line ML training instance. And I just mentioned before why float32 is important, so getting 5x higher there is quite significant. Now let's go into an interesting feature that we baked into Trainium. One of the most significant contributors to accuracy loss during training is the rounding operations. And most computer platforms today implement a form of rounding that is called round nearest even. And that's very similar to what all of us learned in school. Numbers are always rounded to the nearest representable value. So if we take an example with integers, 0.9 will always be rounded to 1, and 0.2 will always be rounded to 0. And at first glance, this seems OK. But here's where it can hurt accuracy. Think about taking a weight value, a parameter value of 1, and a gradient value, or a parameter update value of 0.2. When we add them together, we get 1.2, and after rounding, we get 1. But even if we add 10 gradients of value 0.2 to a weight value of 1 and perform rounding after each step, the result is still going to be 1. And here you can intuitively see that we lost some precision. We would expect that if we add 10 gradients of value 0.2 to a weight value of 1, we'll get a result that is closer to 3, not to 1. With stochastic rounding, this problem is resolved. On every rounding step, we round either up or down in a probabilistic manner, according to the relative distance from the two nearest representable values. So in our previous example, 1.2 will have 80% chance of being rounded to 1, and 20% chance of being rounded to 2. And over large floating point calculations, just like we have in machine learning, this tends to average out and provide with more accurate results. Trainium fully supports in hardware both round nearest even and stochastic rounding, and it's your choice which rounding mode to use. But we saw that if you select stochastic rounding, you can speed up some models by up to 20%. And this is super easy to use, by the way. You just set an environment variable with your preferred rounding mode, and that's it. Trainium takes care of the rest. Now let's look at a real-life example of the benefits of stochastic rounding. Here we have a loss convergence graph on the left and a throughput graph on the right. And our goal is to minimize the loss value during training, while at the same time maximizing throughput. We start with flow 32 in blue, where loss convergence is great, but throughput is naturally suboptimal. It's slower to perform computations in flow 32. Then we move to bfloat 16, round nearest even, in red. And as you can see, throughput improved a lot, but loss convergence is not as good as it was with flow 32. And finally, we go to bfloat 16 with stochastic rounding, which we just discussed. Throughput is just as high as bfloat 16 with round nearest even, again, because Trainium natively supports stochastic rounding in hardware. So you don't need to do anything, any extra compute, in order to perform that form of rounding. But the interesting part is that the loss convergence now looks almost indistinguishable from flow 32. So you truly get the best of both worlds with bfloat 16 and stochastic rounding. We launched TRN1 just a few months ago, and we're seeing strong customer adoption, along with the partners that are working with us to build the infrastructure for new hardware systems for training at scale. PyTorch specifically is working very closely with us, and there are other sessions where we go into details on that. All right, so let's wrap up. First, thanks for spending the time with us today to discuss the custom chips that we're building at AWS. This was a pretty brief overview, and we're very early on our journey. We keep building more chips to provide you with more value over time and across services. Our main message for you today is that the reason that we're building chips is to provide you more value, and we work diligently to improve performance, better our cost structure, and increase our security across the AWS services. We're already working on our next set of chips, so we're looking forward to talking to you next year to talk about our progress and share the new offerings that we have. So thanks, folks. Don't forget to fill the survey, and we'll stick around if you have any questions. We'd love to chat with you.